Hi you guys. So now we're going to solve a problem with Coulomb's law, but with a system of charges. So system of charges here basically means we're dealing with more than just two charges in our system. And we're going to be dealing with the simplistic situation of the charges being along one dimension. We're not going to get anything more complicated than that. Right, so here in this problem, we want to find the net force acting on the rightmost charge, Q3, due to the other two charges. Now, one thing I'll note here is they don't mention what type of force we're looking for, but we're going to assume we're dealing with charges that the gravitational force is negligible. Right? So here the dominating force is the electric force, and this is true when we get into systems or small systems here. So when the objects are very close together, they don't have much mass. When we're dealing with charged particles, generally we're dealing with particles that have negligible mass. So here we want to find the net electric force acting on the rightmost charge. That is to say, charge Q3 in our system here. And if we notice here, there are two charges here that can exert an electric force on Q3. Right, so we're given the charge values of each of these charges as well as the distance in between these charges. Right, so if we want to find the net force acting on charge 3, right, so we know there's going to be a charge on our third charge caused by our second charge, right, so we can write that as a charge of Q2 on Q3. So I'm going to write that as not 23, but the force that charge 2 exerts on Q3. That's a vector quantity. And we add the force that Q1 exerts on Q3. So I'll write that as F13. So the force that charge 1 exerts on Q3. So the net charge of this field is going to be the sum of these two charges, right? So this actually here, that we call this superposition, right? So very similar to what we talked about in waves in terms of superposition of waves. We can also create a superposition of forces. So we have, and that's basically net force. So we've done this before, nothing new. But now we're applying a new formula here. So just be careful here because now we have to worry about direction. And there's a couple of ways we can go about this. But the way I recommend is to find the magnitude of these forces first and then worry about the direction separately. So let's first solve, let's say, the force that charge 2 exerts on charge 3. And I'm going to worry first here just about the magnitude of that force, right? We know that's going to be using our formula of K, our first charge, which I'll call Q2, our second charge, which we'll call Q3, divided by the distance in between them squared. So I'll just call this R with the subscript 2, 3. We square that quantity, just to say that's the distance between charge 2 and charge 3. Right? You don't have to get that specific, but I don't know, call me neurotic, I don't know. Okay, so in dealing with this here, let's see, let's write up in normal numbers. So K, we know is 9 times 10 to the 9 Newton times meters squared over Coulomb squared. Right, that's just the Coulomb constant. We can find that on our formula sheet, on the AP exam formula sheet, as well as this formula in general. Q2, all right, Q2 here has a magnitude of 3 microcoulomb. Ooh, let's convert that to SI units. All right, so micro here is times 10 to the negative 6. All right, so 3 times 10 to the negative 6 coulombs. So notice here I'm being kind of not very nitpicky with sig figs. And then Q3 here, here we are told it is a negative quantity, right? But I am not going to worry about that negative sign. I'll worry about direction afterwards. So I'm just plugging in the magnitude of our charge. So we have 4 times 10 to the negative 6 coulomb. Right, divide this by the distance in between these charges. All right, that's 0.2 meters. And we square that quantity. Right, so doing this math, let me look at my notes here. That force has a magnitude of 2.7 newtons. And let's think about direction. All right, so if we're analyzing the forces acting on this rightmost charge, out of frame, there we go, on this rightmost charge, right, this is positively charged, this is negatively charged, that means they attract. All right, if they're being attracted, that means Q3 in theory wants to move to the left here. It can't because we're dealing with electrostatics here. We're looking at a moment in time where we're not dealing with that. But it wants to move to the left, right? Since it's feeling an attractive force, that means our force is leftward. So I'm going to put my vector sign here to say I'm specifying direction. And I'll say that's 2.7 newtons to the left. Another way to do it, instead of saying left or right, is signifying which way we're going to call positive. So if we wanted to, we could call the rightward direction positive, in which case this 2.7 newtons would be a negative quantity. All right, but moving on. So let's look at the force that Q1 exerts on, Q3. All right, let's first find the magnitude of that charge, that force. All right, so this time we're dealing with K, first charge Q1, our second charge is Q3 this time around, divided by the distance between those squares. That's the distance between charge 1 and charge 3, and we square that quantity. All right, so here dealing with the same K, 9 times 10 to the 9 Newton times meter squared over Coulomb squared. All right, Q1, we're told, is -8 microcoulomb. Here I'm going to plug in the magnitude, worry about direction later. So we're left with 8 times 10 to the -6 coulomb. All right, in Q3 here, again, we have 4 times 10 to the -6 coulomb. That's the magnitude of the charge. All right. And then here, dealing with r squared, the distance in between the two. So now we have to be careful, right? The distance between Q1 and Q3 is going to be these two distances added together, right? So 0.3 plus 0.2 gives us 0.5 meters, and we square that quantity. All right, so once we do that, this force here, the force between charge 1 and charge 3, ends up being 1.2 Newton. Right? And now we think about direction, right? They're both negatively charged. That means they're going to repel. That means Q3, if we're dealing with just these two charges, gets pushed to the right or wants to move to the right. So this force here is going to be to the right. All right, and if we called rightward positive, then we could have said this is just a positive 1.2 newtons. So we're dealing with our net force. We're dealing with, so our first force here was 2.7 newtons to the left. And we add to it our 1.2 newtons to the right. All right, we add those together by adding, since they're different directions, they actually subtract from each other, and we end up with the net force of 1.5 newtons. And then looking at direction, the left direction is bigger, so our overall force is to the left. All right, so that's how you deal with a system of multiple particles, right? You basically are going to be dealing with as if you had a system of just those two particles at a time, and then find the net force between them. Oops, sorry about that. So first we imagined we just had a system of these two particles here next to each other, all right, found that net force, and then we imagined if we only had a system of these two particles, right, found that net force, and then in the end we just took those forces and added them together vectorially. Right, so that's how we can deal with a one-dimensional system of multiple particles. So I just wanted to touch base on the type of system we won't be dealing with in class, but if you want to, they're actually pretty fun to solve if you're, into solving math problems as a hobby. You could actually solve a two-dimensional type quantity. So what do I mean by that? So here actually, I have the Giancoli textbook. All right, but we could solve a problem if we wanted, if we had, oh geez, hard for me to see with the viewfinder. Okay, that is not crooked, hopefully. If we have, let's say, a charge here on our y-axis, a charge here, let's say at our origin, and a charge over here, right? So rather than being all along a line, we're dealing with a two-dimensional space. And the math behind this is very similar to what we just did, except we have to break it up into component vectors. All right, so whenever we have a charge here, we can break it up to be in x, y components, and then find our net force in the x direction, net force in the y direction, and then find our resultant next force by doing a little bit of trig. If you want to know the details on how to do that, you can find other examples online, or you can ask me in class. All right? Whoops. Have a good one, everyone.